Welcome to this video on planning to teach for multiplicative reasoning. My name is Catherine Darwin and I'm a secondary mastery specialist. In this video, I want to talk to you about how we get students to understand that any two numbers can be connected by a multiplicative relationship with one single multiplier. That is going to take various different steps. The first one is the use of proportion as a verb rather than a noun. Students will be used to being asked questions where one thing is as a proportion of another. That might include writing things as fractions or writing things as percentages. However, we want to move them on into thinking about proportional relationships where things are in proportion to one another. This means that they need to shift their thinking from the use of additive relationships to multiplicative ones. We need to be thinking about the things they've learned in Key Stage 2, which include talking about things as lots of and with scaling. We also need to consider that those relationships need to be maintained through multiplication and division only. This can include using the unitary method and using multiplicative relationships to build upwards and downwards. What we do eventually want to do though is bring those multiple steps down to the use of one single, potentially fractional multiplier, and that's the hardest part of all of this. Before we start our planning, it's really important that we start to think about where things can go wrong and how we can plan to avoid those. For me, there are three different places. The first is looking at those relationships as additive only. We've mentioned this earlier that lots of students may have seen scaling in some contexts, but it's not as frequent as those additive ones, so it's important we give them that exposure and so they can see the difference between the two. There is lots of students that also have difficulty working with non-integer multipliers. It may be that students tell you that they can't divide because something isn't a multiple or a factor, or they can't comprehend that you can multiply by a fraction. In either of those cases, that is just a limited earlier experience, and we just need to work hard to undo that. This last one is the biggest one for me, that multiplication always makes it bigger and division always makes it smaller. Again, this is a limited prior experience. From their early exposure to this concept, this is something that we do with them. We talk about sharing and grouping, or lots of. But we know, as mathematicians, that that is not always the case. And so we need to make sure that we're working hard to expose students to those areas where this is not true. The first two of these I'm going to highlight in the next section of the video, but the third one is going to form part of my teaching sequence, and so I'll come to that later on. The first big misconception that students hold is that these relationships between numbers are always additive and only ever consider differences. One of the best ways I've found of seeing if students hold this is to check by asking them to describe sequences. In my first three sequences here, I have got a linear relationship where I'm going up or down by adding and subtracting the same number each time. Students usually found these quite straightforward, but then I need to move their thinking on to looking at multiplying and dividing. So I'm showing them a series of geometric sequences for the next three questions. It's really important here to see where the student's thinking goes from, oh, I'm adding 1, then adding 2, then adding 3, and so on. And can they develop that to seeing that we are multiplying by 2, or multiplying by 5, or dividing by 10, or multiplying by 1/10 in between every single term. The last one is a little bit more of a curveball, again, just to see if they can appreciate that those square numbers are very different to the ones that they've seen before. Another way to check for this misconception is to show students something like this. Showing them two things of different length and asking them to compare them, it's really important to see whether they discuss that this is 1.5 metres shorter or longer, or whether they consider that A is half the size of B, or that B is twice the size of A. It's important to mention that this is just one simple example. You could, if your students aren't so comfortable with decimals, consider just using integer measures here. So we could have A as 1 and keep B as 3. We could take A as 1.5 and then put another decimal in if you want to push their thinking on further. For example, looking at 4.5 metres for the length of B instead. For me, the next step is just checking if we've got difficulty of working with non-integer multipliers. You often find that this one goes hand in hand with the previous misconception, as students fall back on additive relationships when they feel they can't deal with non-integer multipliers. In this case, I might change my previous example just to include one of those non-integer multipliers. Here I'd be looking to see if students fall back on their additive understanding of adding an extra metre and a half, or can they see that this is 2.5 times as long? I'd then be thinking about changing the numbers again. Is it easier or more difficult for your students to see that if I change this to 50 centimetres and 125 centimetres? What if I mix those units up and I had 50 centimetres and 1.25 metres? What if I changed to 2 metres and 3 metres? Would that be easier or more difficult for your students to see? What if I had 2 metres and 5 metres? Or 10 metres and 25? Which of these would it be hardest for them to see and why? Use this for the rest of your planning. At this point, I think it's really important for us to think about the expectations of our students. It's likely in secondary that your students will have seen all of these things in Key Stage 2. However, it's really important to notice the limitations that are placed on Key Stage 2 thinking. Students only often deal with integers or unit fractions. The aim of Key Stage 3 is to push that thinking on further, and therefore we need to make sure that we build on this prior experience. It's really important that we consider prerequisites that form part of our Key Stage 3 curriculum as well. Before we are teaching this multiplicative reasoning section, we should make sure that students have a solid grounding in multiples and factors, use of ratio for unequal sharing, and then lots of grounding in arithmetic with fractions. If you're interested in any of these things, particularly those fraction sections, there are a number of videos in our Preparing to Teach series that already exist, for example, equivalent fractions, or will be coming in the near future, for example, lots of that fraction arithmetic. For me, the most important prerequisite is multiples and factors. Later in this unit, I'm going to be expecting students to be comfortable with using non-integer multipliers to describe a proportional relationship. But first I need to make sure that they're absolutely secure in their knowledge of integers as multipliers in multiplicative relationships. The way that I do this is to use family of 4 calculations and part whole models to ensure that students appreciate relationships between factors and products. Here I'm going to start with the relationship between 2, 3 and 6. I'm going to start by covering up 6, the product. And I can see that I'm looking at the multiplicative relationship between 2 and 3. I can see that 2 and 3 are factors of 6, or that 6 is the product of 2 and 3. That therefore gives me 2 multiplications. 2 multiplied by 3 giving me 6, and then using commutativity, 3 multiplied by 2 also giving us 6. If instead I choose to cover up one of the factors, I'm looking at the multiplicative relationship between 6 and 2. So this time I'm looking at a way to make the factor pair that gives the product of 6. If I already have 2, I need 3. Therefore, 6 divided by 2 gives us 3. And in the same way, if I cover up that 2, I'm looking at the multiplicative relationship between 6 and 3. I need to make a product of 6 with 3, therefore the missing factor is 2. So 6 divided by 3 gives me 2. I can move student understanding on with this by omitting different parts of this part whole model. For example, I could start by just omitting the product, or I could omit one of the factors and ask students to create the family of 4 and improve their fluency in these calculations. Our next step is ensuring that students are really happy with division as multiplicative inverse. Now, lots of students will be perfectly happy with saying something along the lines that the inverse of multiplying by 2 is dividing by 2. But we want to bring that up to speed with our fractional multiplication and introduce the inverse like this. This is just an axiom of maths, and so it's something that we need to be able to build confidence with students using. The inverse of multiplying by 2 would be multiplying by a half. Multiplying by 3 has an inverse of multiplying by a third, and so on and so on. If students understand this, the next section of our multiplicative reasoning is much, much easier. This next section, where we move on to looking at fractions and their reciprocals as inverses of one another, is much more difficult for students. But the rest of our teaching here should allow for students to develop this generalisation for fractional forms as we go through the topic. These could be used as STEM sentences for students to ensure that they are really comfortable with this as a concept. The next prerequisite covers scaling and ratio. Lots of students will have seen this not only in Key Stage 3 parts of the curriculum, but also in Key Stage 2. And actually the level of the thinking that they needed at this point is much higher than we probably think. One of the best places to look for those things is previous SATs questions or in lots of Key Stage 2 schemes of work. Maths for Everyone has got a huge number of these, which cover anything from your basic similar shapes problems to things that are slightly more complicated and require a lot more problem-solving skill. It's really important to note that some of our students will have already seen ratio problems in Key Stage 2. However, the difference being that in Key Stage 2, they are not seeing any formal notation. This use of the language for every is really, really common. So for example here, Mari is playing 5 new songs for every 2 old songs. This is their way into a multiplicative relationship and therefore something we can use to bridge the gap in our multiplicative relationships here. It's also really important to note that these proportionality problems, for example in the context of recipes, are really, really common. Therefore, students will have some concept of these multiplicative relationships already, albeit it is likely to have been for integer multipliers. It may be that you want to go deeper on this understanding of scaling and proportionality with your classes, in which case there are a number of really nice, rich problems from the Enrich website which could help us to do this. One of my favourites is mixing lemonade. However, there are also some on pumpkin pie and orange drink. Each one of these is designed so that it will be an in-depth problem and therefore draw out more misconceptions that your students have with these multiplicative reasoning relationships. Our next most important prerequisite is making sure that we've got a solid foundation with fractions. It may be that you want to start here with equivalent fractions, in which case please look at the other video in our series. I'm going to start at that misconception of difficulty working with non-integer multipliers. For me, the best place to start for this is looking at diagnostic questions. I love diagnostic questions because those questions are designed by subject specialists to really pull out any misconception that our students may have. They also go hand in hand with explanations of where those misconceptions can come from, so you as a teacher can plan to undo those in your teaching. Here I want to be checking for our Key Stage 2 and Key Stage 3 knowledge on fractions. So I'm going to start by looking at proper fractions being multiplied by an integer, and then move on to 2 proper fractions being multiplied together. I then want to move on to looking at fractional division, again with integers to start, and then looking at unit fractions. It may be that we then want to assess our knowledge on mixed numbers and improper fractions in multiplying and division circumstances. If we can find the very specific difficulties that our students have with fractions, it's going to make the next section so much easier. We're now going to turn our attention to the teaching of the topic of multiplicative reasoning. For me, the topic itself starts with this misconception we highlighted at the beginning, that students think that multiplication always makes a number bigger and division always makes a number smaller. We know that this isn't true as mathematicians, but unfortunately the early and limited experience of teaching of multiplication and division often hammers this misconception home. We just need to undo that by exposing our students to places where this isn't true and getting them to think really deeply about why that is. One of my favourite resources for this is the related calculation sheet from MathsPad. Quite often this one is used by lots of teachers when they're thinking about multiplying and dividing by decimals. However, I found that using this with very specific questioning can get students to focus on the idea of relative size compared to the relative size of the multiplier. The variation in this resource is absolutely fantastic. In each section, one number is kept the same, and then each one of the other numbers, the multipliers, is adapted by multiplying or dividing by 10 each time. If you then focus students' attention on how that impacts the answer, you can really quickly get students to appreciate that this multiplication is not always making the number bigger. It may be that at this point you want to ask them to generalise. Maybe you want to get them to consider multiplying by 1. Maybe you want to get them to consider multiplying by 0.1 or 10, and then generalise that even further into what's happening in between each stage. When do these numbers get bigger? When do these numbers really get smaller? With a few more bits of scaffolding, it's perfectly possible to move students onto something like this. There is an entire sheet dedicated to these kind of problems on Teach It Maths. These accelerate students' learning from thinking about just the plain multiplications, where one number is changing, to where two of them are changing. It then pushes them even further in their thinking to consider divisions and what happens when the divisor is changing too. Again, this may need some scaffolding before your students are able to get to this point, but it is a really, really nice way of getting them to consider whether multiplication is always making things bigger or whether it's really making them smaller. We can also combat this misconception by using some similar questions to those from the NCETM PD materials. This one is taken from section 3.1 on multiplicative reasoning. It is one of my absolute favourites from this section. The PD materials come with lots of guidance on how we can use these in lessons or in professional development. Here we are told about the variation, the language, and how to use this in professional development settings. In the variation section, it's highlighted that the number 1142 is picked purposefully so that students don't calculate. It's really important here that the students are thinking about relative size of the multiplier rather than what the answer is. The language here is also really important, and this harks back to the things that they were looking at in Key Stage 2, looking at things like 2 times as big or twice as many. It might also be important here for you to consider whether this really teaches what you want. We need to look at that tipping point of a multiplier of 1. These are just a guide of the kind of questions that you may want to ask your students. So it's not that we can just lift these off the page and give them to them as a set of questions. How would you use them best in your teaching? How could you use the ideas here if you don't think these particular questions suit your class? Once we've undone that misconception, we need to move on to linking two numbers by multiplying and dividing. My favourite way of doing this to start off is introducing a broken calculator task. This tells students that only certain buttons on their calculator work and gives them a target number to reach. In this case, I'm going to tell them that only multiplying and dividing is possible on their calculator. And I normally start by giving them the number 100, as this is quite a familiar number from working with things like percentages. I always then give a start number that is a factor of this number, so that we can really easily do the first few questions. And then we'll build up using multiples of factors of those numbers so that they can work backwards to a factor they know and then build back up again. It may be that we then want to think about unitizing. So for example, in the case of that 21 at the end, we need to divide by 21 before we multiply by 100. This is a really important factor in our multiplicative reasoning. Don Stewart also has a number of tasks on his website based on this principle, where he adds extra constraints. So here is one where we have to use 2 steps every single time. I can only use multiplication and division with digits. Another fantastic resource for this comes from Don Stewart. Don looks at linking two numbers by multiplication and division once again, but this time with a slightly different visual representation. He does this with various different numbers, showing lots of different ways that we can work with them, and then begins to create very similar images to our ratio tables, but he calls them boxes. For me, this is an absolutely brilliant introduction to using ratio tables, which is going to be absolutely invaluable in the next section. I've just translated the final boxes example into a ratio table, and then we can show students that the links do not only go across this way and this way, but instead down and up the box. I've also developed that reasoning slightly here so that I can see that dividing by 3 and timesing by 4 is the same as multiplying by 4/3, and that the reverse would be multiplying by 3/4. So this again is using that idea of inverses that we saw earlier on. It may be that this needs some extra scaffolding. I'm going to talk through that now. There are a number of visual representations that can help students to understand multiplicative relationships. Here I'm going to talk about the 3 that I commonly use in my lessons, which are bar models, scaled number lines, and ratio tables. There are a number of others which you may want to consider, which you can find information on in our supporting documentation and the PD materials. I'm going to start with an example with 2 numbers that have a clear integer factor that we can spot. This helps students to build familiarity with the concepts before we move on to things with multiple steps or a single fractional multiplier. Here I'm starting with the numbers 6 and 3. I'm going to begin by showing them as bar models, because I want students to appreciate the proportionality before I move on to more abstract representations. I want students to understand that bar B is made up of 3 of the same size boxes that make up A, and I want them to understand that A is made up of 6 of the same size boxes that make up B. From here, we can then use the Key Stage 2 language of as big as to be able to link these two. Here I find that B is half as big as A, and A is twice as big as B. I then want to move this into more numerical statements so that I can see that B is half of A and A is 2 of B. This would then allow me to represent this as a multiplicative relationship where we replace the of with a multiplication. My scaled number lines work really similarly because I'm looking at the relative length of each one of these. I'm hoping that students will be able to see that we need to double the size of the number 3 vector to make it the same size as the 6. And then we would need to half the 6 to make it the same size as the 3. My ratio table works really similarly. The first thing I've done is taken the 6 to 3 and then reduced it down to 2 to 1. This allows me to see the multiplication by 2 a lot more clearly, and then the multiplication by half even more clearly still. But it's important that students have been able to grasp the concept of multiplying by 1/3 or multiplying by 3 to get this relationship in the first place. The next step for our students is to think about what happens when I have non-integer multipliers. So I'm going to start here with a bar model that's got 7 boxes representing A and 4 boxes representing B. I've chosen 7 and 4 here because their highest common factor is 1, and that's going to force our students into unitizing. I might later show them relationships where we can be more efficient, for example, looking at things like 6 and 4. But here I want to really have that focus on the fact that 7 of the 4 boxes that make B make A, and 4 of the 7 boxes in A make B. Or to put that more simply, if I break B down to 1 box by dividing by 4, I can then multiply up by 7 to get A. Or I can work the other way around and divide A by 7 to get to 1 box, and build b back up by having 4 times as many, or multiplying by 4. The same idea holds for our scaled number lines. I'm going to ask students, rather than thinking about one step from 4 to 7, to think about a middle ground of moving to the 1 and unitising here. So students should be able to tell me that I need to either divide by 4 or multiply by 1/4, and then multiply up by 7 to get to the length of 7. We could then think about going in reverse and multiplying by 1/7, and then multiplying by 4. The ratio table is going to take this structure and condense it into something that's a little bit more efficient and streamlined. So once again, we can move from our 4 to our 1 by multiplying by 1/4, then from 1 to 7, multiplying by 7. And then in reverse, from 7 to 4, we can see the same thing again, multiplying by 1/7, and then multiplying by 4. At this moment in time, this is sufficient understanding for our students, though we do want them to move on to being able to write these as one single multiplier instead of 2 steps. The final step is to start pulling these ideas together into one single multiplier. With the bar model, we can then start comparing and contrasting these bars to one another rather than breaking them down and building them back up. I can actually see that B is 4/7 of A. I can physically see that in our picture. Seeing what A is in comparison to B is quite a lot more difficult. But if we treat that B as 1 whole 1, we can literally see that it is 1 whole 1 plus 3 extra boxes out of the 4 needed. So we can either see this as 1 3/4, or we can see it as 7/4. I then can use the same kind of logic that we used earlier on to move from our unitary methods to connecting these and seeing these 2 steps combined would be multiplying by 7/4. Or I can work the other way around, and I can see that multiplying by 1/7 and multiplying by 4 would be the same as multiplying by 4/7. This same relationship can then be shown in our ratio table with our 2 separate steps. But then we consider one full step all the way from 4 to 7. And combining that 1/4 and 7 again, we can get to 7/4. And then the same holds in reverse. By considering one large step, we get 4/7 as our multiplier. The PD materials have got another brilliant example of how to assess the use of these multipliers in section 3.1. These are a set of intelligent practice questions that assess student understanding of using these fractional multipliers, but they do it in such a way that students have to think about the differences between every single question. My particular favourite points of these are question C, which looks at the multiplicative identity, any of the questions that involve the use of 0 as a disruptor of student thinking, and also any of those that have infinitely possible answers, as this again leaves an avenue into looking at equivalent fractions. These may not be things that you want to use as a whole with your class. Again, these are things that you may want to take and use in certain sections of your lessons, or use the ideas behind them to get students to think very carefully about what these multipliers look like when they are fractional. For me, multiplicative reasoning is one of the most important topics we can teach well at Key Stage 3. This is for 2 reasons. The first being that ratio and proportion is directly underpinned by it, and this forms 25% of the foundation tier and 20% of the higher tier at GCSE. However, the more I look at the curriculum, the more that I can see that all the way through Key Stage 3 and Key Stage 4, there are a number of things that multiplicative reasoning underpins. And therefore, we're giving our students a head start on topics like these when we teach it well. Fractions, decimals and percentages conversions, equivalent fractions, percentages including growth and decay problems, enlargement and similarity, trigonometry, which is extensively covered in 3.2 of the PD materials, compound units, iterative processes, geometric sequences, gradient and rate of change, and stratified sampling, to name but a few. Please bear this in mind while you're planning this topic, and I hope that this video has been useful.